Good morning. We're going to go over a CAD simulation package for model rockets. There are a few out there. Some are a trial and then paid product, around $100. But OpenRocket is a open source, i.e. free, but takes a little bit of work to master. So this video will help you get started. Um, OpenRocket comes as a jar file, which is a Java. So you're going to need your Java runtime added to your Windows. I'm running Windows 10. I'm going to double click on OpenRocket jar, and up comes the in my particular system. I'm running some the Intel graphics drivers. These errors pop up. Um, and then the package will start. So you can see it's comes up as a in the rocket design mode. So there's basically three modes: rocket design, your motor configuration, and then flight simulations. Okay, so let's just go through a base setup here. Um, so under File, what we have is your new open recent, open example, um, and some printing functions. Under Edit, Scale, and Preferences. Under Preferences is the first thing I change. So, in order to have any really simulation package to work, you need to have a file. And what they are looking for is a RASP motor file or a RockSim engine file. Now, RockSim is a paid product, but again, we're going to show you here how to do some RASP motor files. You can build your own, or you can come to my site and grab a few. So what I've done here is I've gone out and told it where to find my file, and kind of stick it under grandkids because it's easy. And I hope I can remember where I put it. Yes. So here I have these files ending in ENG. I have one mainly for my SD. So let's just show you what's in it. And we're going to do a view. Actually, we're going to add it. So let's bug out here to a text editor and just show you what's in there. Okay. Engine file. Let's see. Rocket. Motor. Looking for text. We're going to go to all files. Let's pull up an engine file. Okay. So we're going to pull up Essie's engine. It's nothing more than a text file. Semicolon is going to be your comment. And here it just tells you where the data is from, when it was produced. And it tells you a little bit about the format. The basic format is it's an A18, a few other thrust vectors, and the manufacturer. And these are your data points, which basically produce a thrust graph. And what people have done is they have a tool. They take the thrust graph, they set the data points, and the tool actually creates the text file. So what I've done here, since I only pretty much work with the B6, the A8, and the C6 type motors, I've condensed one. And all this data comes from an area called thrustcurve.org, and we can go over that later. But be precise, to keep it summary, you're going to need an engine file. You probably want to get the latest data, and that's all it is. It's pretty simple. So there you go. So we've done that in the design. I don't really change much here. In the simulation, I haven't changed much there. Again, there's a lot to change here, a lot of things. Under launch, I've been using the standard atmosphere. Again, you can change latitude, where your launch site is, your altitude. All these things are really going to matter in simulation, such as wind, your barometric pressure, and your temperature. Everything affects flight. It's very interesting. For units, which is nice, is I go to inches because I'm a imperial kind of person, or standard, and then there's metric. So this package covers both. Materials, very nice. You can add your own, but they have a nice selection of basic materials, their type, their density, and their weight, which is really interesting. So as you build your rocket, it's calculating weight, which obviously is important for how high it's going to fly. Graphics, I haven't changed anything here. I leave these two on. And again, that's all you do. So really, you just need to load up the file. Now, if you really want to build something, let me just give you this quick overview, and then we'll do another video on build. Under on edit, you saw the preferences. I haven't gone into component analysis or optimization yet. They'll be separate. But there are some formulas in there that'll take your basic rocket design and say, hey, what can I do to make this really fly in a tuned up optimization? And then there's help and your bugs. So again, pretty decent package for open source. The gentleman that created this, let's just give him some credit, is Sampo, and he was the main developer, and he did this for his master's thesis. So look, you can actually have fun and do something for other people. Obviously, you can see he has a pretty good team there, and a bunch of people that jumped in there and translated it for pretty much every major language. Um, The one thing you're going to notice about model rockets, there's pretty much three divisions. You got the regular model rockets, which pretty much any of us can do, keeps our cost point low. Once you get up to like E-size class motors, you're starting to get into what we call, medium level. Once you get up to H and G, you're looking at what they call the high powered. In high powered, you have to be certified. You're talking much more speed, much more risk, um, things like electronics, altimeters, things that will pop out a drone chute and then the main chute. There's a lot more going on when you get bigger and badder. But it just shows you can have a lot of fun small, or if you want to take it bigger, there are contests, there are school programs, there are big teams. You can have a lot of fun. So that's your reward. This package will take, after you watch my little review, should help you out. But this is just the first step. So let's just look at a recent example. And what we're going to do here is we're going to look at a under mine, we're going to look at the upper half of the mongoose. So when I say upper half of mongoose, the mongooses are two-stage. So the first thing you're going to have to do is measure things. That's correct. You have to measure every one of these components, and these are all set here. And when you click on them, you can see what you have to put in. So you have to measure things. There's sliders to help. Component material, your type of finish, which then matters when it comes to all your optimization and where it's going to go. What you can see here is the main chute, our lugs. These symbols here, this is center of gravity, and this is your center of pressure. The difference between the two is called a caliber, and that's how we figure out stability, if it's really going to fly. You can see the same thing. We have a caliber of 1.58. Our center of gravity is 11.8 inches, and our center of pressure is 13.3. Basically, the rocket rotates around the center of gravity. The closer these two get together, or if this goes above, you do not have a stable rocket. And it won't spin, go around, do some funky things. But you can see it's a pretty decent little package. It also gives you some estimates right off the bat. Your max acceleration, your max velocity, and all these feet per second you can convert to miles an hour, but you already know that Mach is around 700, so we're cooking. And this gives you an actual height of 702 um, with our particular mass. And in here we know we're running a C6. So we've got the rocket design, we've got motor configurations, and I'll go in the next video on how to set this up. It's not real intuitive, but I figured it out. And then you go into your flight simulation. So here, when we do our flight simulate, I just ran one. It tells me the how fast it's going off the rock, how high it's going to go, your optimum delay. So that's that delay on the end before you pop the chute. Now, reason why it's important is if this thing's flying in there at 120 or more mile an hour, you pop the chute, it's putting a lot of stress on the chute. So what the delay does is allow the rocket to slow down and also keep cruising and make actual height, velocity, max acceleration, how many seconds it takes to get to the top, how long it should take to get you all the way down to the ground, and your ground hit velocity. Here it's again, we're using a streamer, or actually nothing here, it looks like. You don't have the streamer put in. So it's still coming in pretty good, screaming from uh, that time. Now, let me show you one more. Again, all this has to be hand entered for every single piece. But let's look at when I built the upper stage. So now what do you see? A little bit better. Again, our same information here, our max. Notice every time we add a motor, there is more weight. And you'll see we're getting a little higher. We have our shock cord and our streamer loaded. And you notice how as we add pieces, the center of gravity and the center of pressure changes, but we still have a good stability of almost 2 calibers. That's what we're looking for. So probably the hardest thing would be a fin. Fins, we have shapes. It's a free form. You can draw the fin. It takes a little time. It's better if you actually have measurements. And you can here go in and change your appearance and blah, blah, blah. They also have some built-in shapes. That's under free form. We also have elliptical and trapezoidal, so you can do some quick analysis. So that's how you would get that in. For your engines, again, we go here and notice I put in all three. So we were shooting a B booster with an A first, a B booster with a C. And then we have a C booster and a C first stage for your maximum altitude. So again, you can run all these different simulations. And so when we run them, let's see what we get. Simulation 7, and it's giving me some warnings because basically I'm going so fast when I pop the chute. It's technically not really good. So we've done all that. Let's go to our okay, so this is our side view. We can go to a 3D figure like that, which is awesome. Again, I haven't looked at everything. Back view, very nice. Probably do a nice fin layout from that. 3D unfinished. Very cool. And 3D finished. So again, you can get a really nice idea here. I have not used every single bit of this package yet. I've only got an hour in it. So when you get a simulation done, you'll see the exclamation point telling me something. I'm going to do a plot export. Now, again, this is a quick summary, so I'm going to click all here, and this is a vertical motion at a time. There are a lot of different things here you can choose from. And you can also do custom. So we're just going to show you a simple plot. And in this one, we have altitude, our vertical acceleration, and our vertical velocity. Because we have a double stage, you'll see there's two impulses. The first stage kicks out, second stage rolls up. And again, really sweet stuff that you can add to your analysis. And this is before you even build or launch. So it gives you an idea. And again, it gets you really into computers, design, and just a lot of nice tools. And again, all free. There's a vertical motion. Ground track is pretty interesting also. Check out this plot. If you hover on things, ground hit, It literally tells you, you can add your winds. It's going to tell you how many feet back. It shows you when you deploy, when you reach different apogees, motor burnouts, all kinds of things when you hover. Again, the team that built this open source product, nice job. So again, I'm going to concentrate on this one. Again, there's paid, there's a few others out there, but this should pretty much give you what you need. So we'll add two more things on how to really just how to build a quick rocket, and how to really just add engines and a few other things that are really not maybe say intuitive, but quicker than reading the manual. Anyway, thank you very much, and that's your quick overview, but I think it shows you to pique your interest. So, when you first go out there and you buy that rocket kit because it's pre-designed, this is how you can go in there and change things, such as change the shape of the fins, or make them more aerodynamic, or make it less, um, make it smoother. There's a lot of neat design here and a lot of reasons, and I think uh, with rockets, I think it's a great way for kids to learn science, get some hands-on, build stuff, run around, and I think anybody that gets into this, still can be some low-cost fun, and you'll have fun too. One last plot I'm going to put in here would be things like your stability. Remember we talked about the caliber, and here is your stability. So we always want this is your caliber, your safety margin basically. You'll notice we never get to 0, and during full flight times we're, above that. So again, most kids in second grade are already learning 2D, 3D, and graphing and data analysis, and I'm not making it up. It's actually in their curriculum. So I think everybody could benefit from this package.